Hi everyone, my name is Andrew Litteken and I'll be talking about improvements in the last year to the IR Similarity Identifier in Outliner. At the 2016 LLVM Dev meeting, Jessica Paquette introduced and talked about the suffix tree and machine outliner. Last year we introduced the IR Similarity Identifier and Outliner that builds on the same strategies and found a 1.3% code size reduction on average in CTMark and is currently in open source. For a review of how we do outlining, please watch these two talks. As a brief review, similarity identification is the process of finding pieces of the code that are performing the same action, like the two highlighted sections here, and replacing the similarly identified code with calls to a new function with the goal of reducing overall code size. So in exploring what to do next with the outliner, we looked at Swift to examine more complexly generated IR. We used Swift UI, a UI framework written in Swift, to track the progress of the optimization. With a simple outliner, we are only able to reduce the code size by 0.04%. One significant omission from the previous outliner were branching instructions, and this kept regions from being large enough to be outlined. So new this year is a scheme to add branches and find nodes into the similarity scheme to make outlinable regions larger. To determine similarity, we start by labeling the blocks each with a sequential number. Each branch instruction has a parent source block and a set of target blocks. Based on the numbering, we can create a graph of outgoing edges labeled with the relative distance to their target blocks. That is, the number given to the target block minus the number given to the current block. So for block 1, we have targets of blocks 5 and 2, which are distances 4 and 1 away. For block 2, we have targets of blocks 3 and 4, which are distances 1 and 2 away. And then for blocks 3, 4, and 5, we have targets outside of the region, and we use a specific identification for each unique block targeted outside the region. Using this graph structure, we can check if the corresponding branch or phi structures in each region generates the same graph structure. And if they do, those regions are compatible to be outlined together. So what new code did we outline from the Swift UI project? One example is repeated code from expansion from Swift performing range checks on arrays. Whenever a programmer tries to index an array, Swift performs a check to ensure that that index isn't out of bounds. This generates a set of branching instructions for each check made in the program. Many programming languages have this feature, and it happens a lot, providing many opportunities for outlining code in Swift and many other languages. Many languages also offer the ability to template a function for different specialized types, such as Swift, C++, and Rust, generating a function specialization for each type. There's a lot of nearly identical code in each of these specialized functions, and it's an ideal case for deduplication if you can work around the differences. Current optimizations, such as the function merging paths, don't look for exact similarity for deduplication across the entire function, and they don't accommodate this granularity. The IR outliner is able to selectively remove the similar parts while leaving the different instructions behind. We also, in addition to the biggest addition of outlining branches and multiple blocks at a time, we added general matching of calls within outline blocks. Where previously both the name and function type of the call had to match. Now for both direct and indirect calls, only the type signature has to match. And intrinsic calls are also now allowed to be outlined, but are still restricted to matching by both name and type signature. After adding the branch outlining, this increased our code size and the reduction in the Swift UI project to 1.27%. And with more generalized call instructions, this increased to 1.9% code size reductions in the Swift UI project. We also tested the outliner on the compile time suite and found similarly beneficial remarks on top of current size optimizations in CTMark, with large improvements and many different benchmarks, specifically SQLite 3, LeetCode, and SPass. We found a 2.2% average code size reduction in CTMark, which is a 70% increase over the simple outliner last year. Most of this work is in open source already, with a few more complex feature directions for the outliner. We'd like to determine ideal location and strategy for the outliner and size-based optimizations. We'd also like to improve our generated assembly code from LLVM that would benefit the estimation of code size reduction, better prioritizing what to outline. We'd also like to expand our matching beyond identity, where we canonicalize the order of operations on certain inputs, flattening the similarity space, giving more opportunities for reduction overall. Thank you for your time. You can reach me or Jessica at our respective emails.